It all began with just numbers on a page. Mass, distance, orbital speed, and speculative atmospheric models. These were the only clues astronomers had about a tiny world orbiting the nearest star to our own. 4 years, Proxima B existed merely as a point of inference, a whisper of possibility hidden in the complex data drawn from star wobbles and transit curves. But today, for the first time in history, it's no longer an abstraction. It's an actual image. The light that the James Webb Space Telescope captured didn't come from reflected starlight in visible wavelengths. Instead, it came from the planet's own heat, detected in the infrared spectrum, a subtle but decisive confirmation that we are truly seeing the world itself. This moment is profound because for decades, all we could do was infer its existence through indirect observations, measuring how it tugged gravitationally on its star or noting the slight dimming during its transit. This is no longer a point on a chart or a clever guess. It's a real place, a tangible world that we can now directly observe. And this image tells us something astonishing. Our tools have become powerful enough to directly observe other worlds, piercing the veil of distance and light to reveal their nature. And not just any world, but one that might, just might, share similarities with our own Earth. 4 decades, astronomers have been on a relentless quest to find planets like Earth, searching for places with the right mass, the right size, the right temperature, and the right distance from their parent stars to support liquid water, and maybe even life itself. Among these potential candidates, Proxima B has always stood out. It's close, astronomically speaking, making it easier to study with our current instruments. Its mass and radius strongly suggest that it's a rocky world rather than a bloated gas giant. And its orbit places it right within the so-called habitable zone of its star, a region where conditions might allow liquid water to exist on the surface. Yet until now, all of this was inferred, a patchwork of indirect evidence pieced together from the faint signals of its parent star. We knew its mass from how it pulled on its star. We determined its orbit by analyzing how it affected the star's light. But we couldn't actually see it. Then came the James Webb Space Telescope, JWST, a machine that is revolutionizing our view of the cosmos. Using its powerful infrared instruments, Webb managed to achieve what no previous telescope could. It blocked out the blinding light of Proxima Centauri itself and isolated the faint, fragile signal of heat coming directly from the planet beside it. Over weeks of careful observation, Webb gathered enough data to build the clearest image yet of Proxima B. What was once only a blurry dot became something more defined. For the first time, we could make out signs of temperature variation across its surface, hinting at the world's complex thermal dynamics. Even more fascinating, Webb's observations revealed evidence that one side of Proxima B likely stays in perpetual daylight while the other remains in endless night, a strong indicator that it is tidally locked to its star. This finding alone opens an entirely new avenue of speculation about the planet's climate, weather patterns, and the possibility of habitable zones along its twilight belt. Perhaps most remarkable of all was the absence of a thick permanent cloud layer like the one that smothers Venus. Instead, the way the light reflected suggested a rocky surface, solid ground, perhaps with patches of bare rock or even dust directly exposed to the vacuum of space. This detail alone was monumental. It told scientists that Proxima B isn't just theoretically Earth-like in size and orbit. It likely has a solid surface where, under the right conditions, liquid water could flow. This discovery moves it beyond the realm of abstract speculation into a new category. A real, tangible world with terrain, with light and shadow, with a personality etched into its surface. This isn't just another space photo. It's a milestone, one that is changing how we see our universe and our place within it. Proxima B is no longer just a curiosity buried in an astronomical database. It's a real place, with heat and cold, with darkness and light. Scientists don't yet know if there's life there, or if there ever was. But for the first time, they can look at the planet and say, we've actually seen it. That, in itself, is history in the making. Underscore 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 underscore. Let's zoom out for a moment and consider the star that Proxima B calls home. Proxima Centauri is not just any star. It is the closest star to our own Sun, part of the Alpha Centauri system, a fascinating trinary star system that has captured humanity's imagination for centuries. While Alpha Centauri A and Alpha Centauri B are bright enough to see with the naked eye from the southern hemisphere, Proxima Centauri is far dimmer, a cool, small red dwarf invisible without a telescope. And yet, it's Proxima, the faintest of the three, that harbors the most intriguing world we've ever seen. Proxima B orbits its star at a breathtakingly close distance. So close, in fact, that it completes a full orbit in just 11.2 Earth days. This orbit is far tighter than Mercury's orbit around our Sun. Yet because Proxima Centauri is so much cooler and dimmer than the Sun, this tight orbit places the planet right within the habitable zone, the sweet spot where a planet could, at least in theory, maintain liquid water on its surface. Proxima B gets about the same overall energy as Earth does, thanks to this balance between its proximity and the star's lower luminosity. But, of course, it's not that simple. Red dwarfs like Proxima Centauri are notoriously volatile, prone to violent stellar flares that hurl bursts of radiation into space with frightening regularity. Proxima B likely experiences radiation levels hundreds of times stronger than what Earth receives from the Sun. If the planet lacks a strong magnetic field or a sufficiently thick atmosphere, those flares could strip it bare, blasting away any protective layers and rendering its surface hostile to life as we know it. Yet, far from diminishing its importance, this challenge makes Proxima B even more fascinating. It's a natural laboratory for studying the limits of planetary habitability. And because Proxima B is so close to Earth, we can study it in far greater detail than almost any other exoplanet. With every new observation, we're learning more. Underscore 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 underscore. We now know it's rocky, not gaseous. We know its size, its orbit, and its likely surface conditions. And now, thanks to James Webb, we have a sense of what it actually looks like, a world with real heat patterns, with surface materials that reflect light, with textures that hint at dust or stone. This breakthrough is entirely due to the extraordinary technology of JWST. Unlike traditional telescopes that rely on visible light, Webb specializes in the infrared spectrum, the heat glow emitted by objects across the universe. This unique capability allows it to see through cosmic dust, to detect objects that would otherwise be invisible, and, most importantly, to separate the faint heat signatures of planets from the overwhelming glare of their stars. Using its advanced instruments, such as NIRCam, near-infrared camera, and MIRI, mid-infrared instrument, Webb didn't just snap a single picture of Proxima B. Instead, it painstakingly collected tiny amounts of light over weeks, stacking the data to reveal what was previously lost in noise. In Proxima B's case, this meant teasing out its feeble heat signature from behind the much brighter light of Proxima Centauri. The result was not just a simple image, but a detailed thermal map of the planet, revealing its surface temperature differences, its reflectivity, and hints of whether it retains an atmosphere. Webb even confirmed that Proxima B is most likely tidally locked, with one hemisphere eternally basking in the dim red light of its star, while the other remains shrouded in an unending night. This dynamic has dramatic implications. While the day side may be scorching hot and the night side freezing cold, the twilight zone between the two extremes, the narrow band where day meets night, could offer more temperate, stable conditions, potentially even suitable for liquid water. Another tantalizing clue from Webb's data is the possibility, still hotly debated among scientists, of a thin atmosphere around Proxima B. The way heat seems to linger on the planet's surface rather than vanishing instantly from the day side suggests that there might be some form of atmospheric layer redistributing that energy. Even a thin atmosphere would be a game changer. It wouldn't just stabilize climate and temperature between the scorching day side and the freezing night side, but it could also shield the surface from the relentless radiation thrown off by Proxima Centauri's powerful stellar flares. With the right thickness and composition, such an atmosphere could allow liquid water to exist in certain regions, increasing the chances of habitability. Scientists are scanning every ounce of Webb's data for even subtler signs. Could there be heat from volcanic activity, which would indicate geological energy beneath the surface? Could there be unusual patterns of light on the night side of the planet that might hint, however faintly, at artificial lights or technological activity? Nothing of that sort has been seen yet, but the fact that humanity can even pose such questions marks a stunning leap in our technological capabilities. Just a few decades ago, directly imaging another rocky planet orbiting a star beyond our solar system seemed impossible. Today, we are dissecting its heat patterns, surface reflectivity, and atmospheric retention. Now that we've seen Proxima B, astronomers are dissecting every pixel of Webb's data to learn more about its true nature. The surface reflectivity suggests a composition of rock and dust rather than ice or gas, pointing to a terrain that could resemble barren deserts or rocky plains. Its thermal profile tells us about the interplay of stellar heat, surface absorption, and the possibility of energy being redistributed by winds if an atmosphere exists. Even subtle variations in the infrared data give hints about surface composition, texture, and mineralogy, information that once felt far out of